We are going to talk about interpreting samples. That means you've conducted a sample, you've got your result, you've got your average, your proportion. The question now is, what do we do with that number? How do we actually make sense of that number in the context of the population? Here's an example to start with. What is the average age of all coins currently in circulation in the United States? I want to point out that would be an incredibly hard sampling problem to do, which is why I haven't been able to find an example where somebody's actually done this experiment. You'd have to consider all the coins being in the cash registers of every retailer in the US, all the coins in the vaults of every bank, all the coins that people have in jars in their homes or in their pockets. How would you actually sample each one of those different populations? Coins that are being held by people who are overseas, coins that are being held by collectors. How would you actually figure that out? Be an incredibly difficult thing to do. But let's pretend, for the sake of the argument, that somebody did it. Let's pretend you had a really good sample, multi-level sample. You randomly sampled banks. You randomly sampled retailers. You randomly sampled people. You checked all the coins that they had. You randomly sampled from among their coins, from out of the bank vaults, from out of the jars, from out of the pockets, from out of the cash registers. At the end, you had 1,000 coins that you felt were actually representative of all the coins in circulation in the US in total. Here is my sample of 1,000 coins. We can pretend that's 1,000. I don't know, might be close to that. And let's pretend that the coins in this jar have an average age of 22.5 years, meaning on average they were minted in the late 90s. Now, what does that imply about the general population? Obviously, if I were going to guess, my best guess would be that the average age of a coin in the US is 22.5 years. I obviously can't do any better than my sample. But what does that really mean? Does that mean that it's between 22.4 and 22.6? Am I confident it's really close to 22.5? Or is it more like between 22 and 23, or more like between 20 and 25? So in other words, how can I estimate the sampling error? Remember, non-sampling error is avoidable. Non-sampling error are things like if I only looked at banks or if I only looked at people, that would be sampling error because I'm ignoring huge chunks of the population. If, for example, I just asked all of my friends who live in San Francisco, a city with a mint in it, therefore likely our coins are newer because they get minted here and they might take longer to get to Pensacola, Florida than they do here in San Francisco. If I just surveyed my friends, I would have sampling error. I'd have non-sampling error. But let's assume we reduce non-sampling error to 0. Let's assume there's no non-sampling error. What we're left with is sampling error, which is this is not a census. I have not counted every single coin in the US, so there's going to be some error in that. I'm going to be a little bit wrong just by virtue of the fact that I didn't actually get every single coin. That's okay, but I'd like to be able to quantify it. I'd like to know how wrong I am and get a range of where I think the true value actually falls. Well, one solution is that sample that I just conducted that took a long time and cost millions of dollars, and I had to survey 100 people. I could do it again and again and again and again and again and again and again. I could do that sample a whole bunch of times with the same sampling design. If I randomly select banks, I'm going to get different banks. I randomly select people, I'm going to get different people. I randomly select the coins in the cash registers, I'm going to end up with different coins. Each sample is going to be a little bit different, and they're going to have a different mean. Let's say I conducted a dozen samples, and these are my dozen sampling means. All of these 12 means are now referred to as the sampling distribution. If I average those 12 means, I now actually have an average of all 12,000 coins in those 12 samples of 1,000 each. That's a really good guess for what I think the actual average age of a coin in circulation is. That becomes a very, very good guess for what that should be. The average of those 12 means, by the way, is 21.95. So I would say I think the average age of a coin in the US is about 21.95. But I can also do the standard deviation of those 12 means. Remember, the standard deviation is the average difference between each data point and the mean. So these data points are centered around 21.95, but they tend to miss that. They tend to be off of 21.95 by about 0.89. That is the standard deviation of those 12 numbers, those 12 means. Our symbols for this, our symbol for sampling distribution mean is mu. Remember, mu is our symbol for average. Subscript X bar. Remember, X bar is our symbol for the average of a sample. So it's average of a population, subscript average of the sample. Our symbol for sampling distribution standard deviation is sigma, which is the symbol for the standard deviation of the population, subscript X bar, standard deviation of the means of the samples. Again, very complicated symbols, but that's what they mean. Okay, so now I can say that my best guess for the average age of a coin in circulation is about 21.95 years. And I think we're probably wrong by about 0.89, but I don't know in what direction. I don't know whether we're too high or too low. A fun side note, it turns out that the sampling distribution is always normal. That if I do a whole bunch of means of various samples and I graph those means, I always get a normal curve, even if the original data are not normal. Coins are probably not normal. There's a lot more new coins in circulation than there are old coins. They wear out, they get lost, whereas new ones keep getting minted. So if I graph the age of every coin in the US, it would not look like this. It would not be a nice, smooth, normal curve. It would be really weighted to one side. It would have a long tail in the other direction. A lot of older coins, or a few older coins, and a lot of newer coins on one side. But if what I'm actually doing is a whole bunch of samples, those samples will be normal, which is handy. So going back, I can say that the average coin in the US circulation is probably about 21.95. That would be that vertical line in the middle, 21.95. And I'm probably wrong by about 0.89. That would be the standard deviation, or the distance out here to the inflection point where the graph straightens out a little bit. That would be about 0.89. In other words, it's between about 21.6 and 22.84, the average plus or minus one standard deviation. Probably, which is a very imprecise word. We can do better. We can do better than the word probably. Remember this? Oh, here's a blast from the past, the 68, 95, 99.7 rule. We learned this way back in January. If you have a normally distributed data set, which we just established, sampling distributions are always normal, then you can say 68% of the data, 68.27 to be exact, fall within one standard deviation of the mean, 95% within 2, and 99.7, almost all, within 3 standard deviations of the mean. That's a handy rule. It's an empirical rule, which means it's not a rule that somebody ever proved. It's just a rule that seems to be true, because it is. So this brings us to something called confidence intervals. Rather than saying the average age of coins in the US is probably between 21.606 and 22.84, I'm going to replace is probably with has a 68% chance of being between those two numbers, or even better, I'm going to say I have 68% confidence. I am 68% confident, a little more than 2/3, that the average age of a coin in the US is between 21.06 and 22.84. So let's just say somebody says to me, Mr. Agnew, that's not very confident at all. 68% confidence is not super confident. I need you to do better. Okay, well, I'm 95% confident that it falls within 2 standard deviations of the mean, which would put it between 21.17 years and 23.73 years. I'm 95% sure of that. If 95% is not good enough, then I can add another standard deviation, say I'm 99% confident, 99.7, that it falls within 3 standard deviations of the mean, which would put us all the way down to 19.28 and 24.64 years. Notice how that range keeps getting wider. The more confident I want to be, the wider a range I've got to give to be pretty sure that I fall within that range. 99% confident is pretty darn confident. So that there I can be fairly sure of it. So there you have it. That's how you take numerical data. We'll do categorical data in the next video. That's how you take numerical data and you take it from your sample to many samples, all the way to being able to say, I am this confident, 68, 95, or 99% confident, that the actual mean of the real population is between this and this.